Patrick?
Hello?
Yeah, hi Patrick, how are you?
I'm doing good. How are you doing?
Good. So, your dad said that he sent some stuff to my email?
Yeah, we just sent it.
Oh, there it is. Okay. 5 pages. Let's see.
The bottom one is page 1.
Oh, okay. Let me do this. All right. And there's just 5 in total?
Yep.
Got record going. Let's have a look at page 1. What kind of stuff are you doing at the moment? Solve each proportion. You have a particular place you want to start, Patrick, or should we just go 1 down?
1 down.
Okay. That's 5. You might have to help me with some of this. It's a little blurry. 5x over 4 equals 35 over 8.
Yep.
Okay. It's my first step.
Well, you could cross multiply.
Okay. So what's my next line?
You could do 5x times 8.
Okay. Just read my next line for me. Your cross multiplying is correct. Go ahead and do it and tell me what the next line is.
Would it be 40x over 140?
40x equals 140. You see why? In other words, when I cross multiplied, this is what I got. I got 5x times 8. I got to cross multiply on the other side also, equals 4 times 35. So that's how I get 40x equals 140. Now what?
Now you just divide by 40.
So x equals 7 halves. Which I can definitely cancel the zeros, and I can divide top and bottom by 2. All right. I like the fact that they review algebra, because a lot of times geometry is a full year subject, and I've found most of my students have forgotten a lot of the algebra they learned. Next line. Do you have a calculator in front of you, Patrick?
Yes.
Okay.
So it would be 75 equals 3x minus 9.
Okay, next line.
Well, you could plus 9 to each side.
Okay. So what's the next line?
So it would be 84 equals 3x.
And the final line?
It would be 28 equals x.
Okay. Only reason I kind of want to insist you do it is because when test time comes, it's going to have to be you that does it. Every step, you know what I'm saying?
Yeah.
Did you get them all done? Mm-hmm. Okay.
Next line.
You'd have x minus 4, 2x minus 4. Then would be 4x plus 16.
Right. What else? What do I need right there?
Equals.
Okay.
Yeah, hold your memory. It's on the carry until you get rid of it. Okay?
Equals what?
4x plus 16.
Okay. Next line.
You could have 2x equals 4x plus 12. Wait, no. No.
First of all, decide whether you're moving your 2x to the right side or are you going to move your 4x to the left side. In other words, I can do either. I can move that over to there, or I could move this over to there. My goal is to get anything with a variable on it on one side and anything with just numbers on the other. So in this case, does it matter?
No.
Okay, so give me a next line. You're right, it doesn't. Either scenario produces basically the same problem.
You could have 2x equals 4x plus 20.
Okay, that's fine. That's an intermediate step, and now what?
Then you'd have 2x plus 20.
Okay, remember you want to get all the variables on one side, all the numbers on another. You don't want to get everything equal to 0. That's what you want if you're dealing with quadratics. But this is strictly linear. We don't have an x squared here. So whenever you're dealing with a linear equation, you want to gather all your x's on one side, all your numbers on another.
So it would be negative.
Okay, go ahead.
Negative 2x equals 20.
Okay, finally, last line.
We'd have negative x equals 10.
If I'm going to divide each side by -2, which I want to do, because I want to get rid of not only the 2, but the negative sign also. In other words, I want to end up with x equals something. So x equals -10.
You see that pattern? Okay, no,
you don't need to do it in 2 steps. You were doing it in 2 steps. I was just doing it in 1 by dividing both sides by -2. Now, notice why it didn't really matter which side you took the x's to. In other words, when I got to this point right here, I usually focus on keeping the coefficient of x positive. So I would have taken the 2x to that side because what I'm left with is a positive 2x. But then the only difference is the next line would be I have a positive 2x over there. Move the 16 to the left, I have a -20. Still get the same answer, -10. And it doesn't matter if the x is on the left or the right side. The reason I choose the x is because I don't know about the numbers yet. But I know if I move the 2x to the right side, I'm going to have a positive coefficient. Whereas if I move the 4x to the left side, I'm going to have a negative coefficient. So that's the first thing I look at, and that's the way I'm going to go. Because at this point, I don't know yet whether the number is going to be positive or negative. If it's positive, then this is the best way to go. If it's negative, then it doesn't matter. I could have gone either way, and it didn't make any difference. But I usually let the terms with the variable decide whether I'm going to move my x's to the right or the left side. Not saying you have to do it that way. It's pretty much a matter of preference. There's really no right or wrong. I kind of use a general rule where if I can eliminate negative numbers, I usually try to do so. And just because you don't make as many mistakes if you don't have as many negative numbers. All right. So we've got the ratio of three angles are in a 5-7-8 ratio. How can I find the measurement of each angle? 5 to 7 to 8. And there's a key concept here that you have to use.
I'm not quite sure.
The introduction of a variable. In other words, if the three angles are in this ratio, then what they really are 5x, 7x, and 8x. If my angles are in that defined that way, then they're definitely in a 5 to 7 to 8 ratio, right? And now the reason the introduction of the variable is important is because now I can write an equation. What does the sum of three angles of a triangle have to equal?
Isn't 360?
It's 180. 180 is
100. That's
the magic
rectangle.
number. It's the magic number in geometry. I mean, it's not the answer to everything, but it's an answer to a lot. And so what equation can I write? All three angles have to add to 180. What equation comes out of that?
You could have 5x plus 7x plus 8x equals 180.
That's it. With geometry, always be looking to write an equation. That's the way you virtually are going to solve every single geometry problem, is figure out how can I write an equation, and then it's just an algebra problem. That's 20x equals 180, x equals 9. So the angles are 45, 63, and 72.
5 times 9, 7.
That's in a 5 to 7 to 8 ratio.
Nice way to solve it.
Now, the whole key on this problem is really the decision to introduce a variable. In other words, I'd have a hard time solving this if I started out that way, because I can't write an equation. In other words, I can't say that 5 plus 7 plus 8, oops, hold on, something's gone wrong with my, one moment. Let me shut this down and reopen another one. I can't say that 5 plus 7 plus 8 is equal to 180, because it's not. So until I introduce, always know that if you're going to have an equation that has to be solved, you're going to need a variable. And so that's where the logic comes from, introducing the variable. And this next problem is kind of similar. The ratio of the measures of the sides of a rectangle are 7 to 8. So how should I label this rectangle?
You have one side 7x, one side 8x.
Good. And its perimeter is 300. So what equation can I write based on the fact that its perimeter is 300?
15x equals 300.
15x is only from there to there. The perimeter is all the way around.
No, 30x equals 300.
So 30x equals 300. Sorry about my digital drawing tablet. I may have to reboot, unplug it, and plug it back in again. So x equals 10, which makes this side 70 and this side 80. So this thing say right there? Oh, find x. Well, notice they asked the question, find x, before we ever even introduced it. So that's a good clue. If you're trying to solve this problem and you look at their question and it says find x, that's a good clue that we want it to be 7x times 8x. Okay. PEA format.
Do 6.
Yeah, we can skip
Hey,
over
David,
6 and
we
go to
can
7.
skip over 6.
And go to 7.
Go to 7.
You sure?
Yeah, 6 is pretty easy.
Are you sure?
Yeah.
You want to do 1?
No, that's easy.
Okay, if you're absolutely sure. Okay, Dave says he's absolutely sure, so
Okay.
just done.
Similarity, you just have to prove 3 angles. In other words, this triangle is similar to this triangle because that angle is equal to that angle is equal to that angle because the parallel lines, and that angle is equal to that angle. Once I have 3 angles that are the same, I know those 2 triangles are similar.
Okay, so that should be covered.
Let's do 7. Based on what you're looking at, what equation can I use? Well, what equations can I write?
You could have x plus 2 is equal to 10, but couldn't you also have x plus 2 over x plus 1 is equal to 10 over 8?
That's better, because you can't say that x plus 2 is equal to 10. That's not equal to 10. If they were congruent, you could say that. But similarity merely means the ratios are the same. Okay? So I can write a couple of ratios. I can say that x plus 2 over x minus 1, in other words, the ratio within that one triangle, is the same as the ratio in that triangle, the long side divided by the short side. Okay? That allows me to solve for x. But it's important to understand other ratios that you can write because they can be very confusing if you don't understand them. Not only can I say that side is to that side as that side is to that side, but I can also say plus 2 is to 10. In other words, the long side of this triangle is to the long side of this triangle.
David?
Yeah.
If you could just hold on a second, let me get the dog out.
Okay.
Oh my God.
Come on. Okay. There you go.
All right, we're back.
It's okay. Usually I'm the one apologizing. I have a small dog also.
Well, we have a herd from my daughter that moved back in, but
Okay.
whatever.
Okay. What I was saying was that these ratios work in lots of different ways. The ratio within this triangle is the same ratio as within that triangle. Or the ratio of the long side to the long side is the same as the ratio of this short side to this short side. So I can write, in other words, both of these are true. And the reason I want you to make sure you understand that is because it's really easy to get confused. Most people think there's only one set of ratios you can use. Notice what happens when I go to solve this? I'm cross multiplying, I end up with 8 times x plus 2. Well, when I go to solve this, I get the same thing, 8 times x plus 2. So the solution is the same. Do you want to go through it, or should we advance? In other words, how much of the algebra would you like to review?
I'm pretty good with the algebra.
Okay. Okay. Let's go to 8. What is true about this triangle with a line MK drawn parallel to this base right here?
They're similar?
Well, you're correct. They create two similar triangles. This little triangle here and then the big triangle are similar to one another. They share that angle. This angle right there is the same as this angle, and this angle right here is the same as that angle because of the parallel lines. So we do have similarity. So what ratio? In other words, whenever you're dealing with similarity, usually the answer is found in coming up with a ratio. What ratios have to be true? And I think in this case, it's almost easier to view them as two separate things. In other words, we have this thing down here and we have this thing here. What ratio would you think, what would be true about the right side versus the left side? This 8 is the length of JK, and they've given 24 as the length of JL, so that means this has to be 16. So that's a first step. That's 8, that's 16. What ratio should be true? Just what would you think, logically?
Would it be x plus 5 is to 8 is 6, x plus 2 is to 16?
Yeah, and in this case, that one makes a lot more sense than trying to do the other ratios. In other words, we're not really viewing this as a big triangle and a little triangle. We're kind of more viewing it as the ratio of this side to that side is the same as the ratio of this side to that side. And then again, that's a simple algebra problem. Did we miss 9? Oh, 9's on the other side. Now this is a triangle with something a little different. In other words, the last triangle we were looking at, this one here, this line MK is not a mid-segment. It does not split this thing in half. Notice this was 8 and that was 16. Okay? In this problem here, what's different about it?
That is a mid-segment?
Because that side's equal to that side, and that side's equal to that side. Therefore, this line is splitting this triangle perfectly in half, so to speak. And I say so to speak because this area is not the same as that, but the side lengths are the same. So, what must x be?
17.5, which is half of 35.
Correct. Correct. And as long as we're talking about this problem, let's also talk about trapezoids. If I chop the top half of that thing off, I get this. Okay? A mid-segment on a trapezoid does the same thing. It makes that equal to that, makes that equal to that, and you find the mid-segment by adding the small base and the top base and dividing by 2, right? In other words, if this is 20 and this is 10, then this has to be 15. Now, the only reason I bring this up is because this is pretty easy to memorize always, and I can apply it to this triangle. In this triangle, the bottom base is 35, the top base is what? 0. So add 35 and 0, divide by 2, and you get your 17 and a half. What ratio can I come up with on number 10?
30 is to 24 is 10 is to x.
Okay. And in truth, you could actually come up with a couple of ratios. I could also say 24 is to x as 30 is to 10. In other words, this is a case where maybe, and incidentally, when we write these ratios, regardless of which one you choose, put x in the numerator. And I'll show you why. If I do it the way you talked about doing it, I'm going to compare that side to that side. But I'm going to do it slightly different. You put 30 in the, you did it this way. 30 is to 24 as 10 is to x. Which of these two equations is easier to solve?
Probably the bottom one.
The top one. Because the variable's in the numerator. In other words, it's all I have to do to solve the top one is multiply both sides by 10. And that's pretty much done. Okay? The bottom one, I have to cross multiply. And then I have to do a second step. Divide both sides by 30. So I get 8 the same way, and cross that off with that. 3 and the 24 equals 8. But whenever you're setting up a ratio, always kind of keep that in mind, that if you can put your variable in the numerator, it's going to make things easier. I don't actually cross multiply in the first case. Notice that I've got x over 10 equals 24 over 30. I don't cross multiply that to solve it. I don't need to. All I need to do is multiply both sides by 10. This one down here, I really do need to cross multiply and then divide by another number. So this is a two-step process. This is basically a one-step process. Just something to keep in mind when you're setting up these ratios. Whenever you see a bunch of parallel lines like this, whether it's a triangle or a trapezoid or a couple of trapezoids. In other words, this thing here is a trapezoid, that's a trapezoid, and the whole thing is a trapezoid. Which means I can analyze it exactly the same way I analyzed the triangles and also the trapezoid that I told you about. So what kind of ratios? Give me a ratio equation.
Could you have 5x is to x plus 2 as 3 is to 12?
Yeah, and here it doesn't matter which is the numerator or which is the denominator. I've got to cross multiply regardless. In other words, I can't do this in one step regardless, so I'm going to cross multiply it and solve it. Let's just every now and then do one of these. What's the next line?
Would it be 60x?
Sorry, what?
60x is equal to? Would it be 3x plus 6?
Next line.
Get a 57x is equal to 6.
Equals what?
6.
And finally, can you reduce that number?
No.
By doing what? How do you reduce it?
3.
By dividing top and bottom by 3, right? I can't divide top and bottom by 6. The bottom doesn't divide by 6. But they both divide by 3. How do I know the bottom divides by 3? Because the digits add up to a number that is divisible by 3. 5 plus 7 adds to 12. 12 is divisible by 3, therefore 57 is divisible by 3. So divide top and bottom by 3, what do you get?
You get 2 19.
2 19ths? Is that what you said?
Yeah.
Okay. Well, I will say this. They know how to beat a dead... No, this is a little harder. This is... Give me some equations.
Would you have...
What are you trying to solve for y? Okay. Well, how about some ratios?
You have 3y is to 2x plus 4 is 2y plus 2 is to 3x plus 1.
Can I solve that?
No,
Why?
because there's an x and a y.
Because there's 2 variables and there's only 1 equation. So for me to be able to solve this, I need to come up with another equation that's not the same as this equation.
Did you have 3y is to 2y plus 2?
As
2x plus 4 is to 3x minus 1.
now let's see if that's the same equation. I'm going to cross multiply that. That's what I got to do there. In other words, it's the same thing, is it not?
Yeah, it is.
Is there anything missing that I'm not seeing here? Is there more information to the right by chance?
No, that's it.
Well, the only way we can find y is as a function of x. In other words, we don't really have 2 equations and 2 unknowns here. The second equation is the same as the first. It may not look exactly the same, but it is. Okay? So, if I'm trying to solve for y, my answer is going to be in terms of x. I can't solve for y, a number. I mean, you can kind of see what the problem is. Whatever number I might put in for y, I'll come up with an x, but I could multiply both sides by 10, and my y would be different. So with this much information, we can't solve for y in terms of a number. We can solve for y, but it's going to be in terms of x, and the algebra is a little more complicated there, so let's go through that. What's the next step?
I'm not sure.
Cross multiply. That's why the 2 equations were the same, was because after we cross multiply, we're looking at identical stuff. Now, this is where it gets a little tough. What's next? What do you always try to get rid of in equations?
Parentheses.
And denominators. We got rid of all the denominators by cross-multiplying. Now let's get rid of all the parentheses.
You could distribute.
Okay, do it.
We have 9xy minus 3.
3y. Right?
Would equal,
Now you have to FOIL these two things.
so we have 4xy plus 8.
Plus 8y. In other words, when you multiply that times that, you get 8y.
So from here you could take away 4xy.
Two more terms.
Oh, two more.
Multiply that by that. That's 4x. Now finally multiply that by that, which is 8. Okay?
Oh, yeah.
So after eliminating all my parentheses, I'm left with this. Now I'm trying to solve for y. What's the next step if I'm trying to solve for y?
Did you take away 4xy?
Every term that has y in it, put it on one side of the equation. Every term that does not have y in it, put it on the other side of the equation. Pretty simple rule. Okay? So what goes on the left?
Would be 9xy. Would it be minus 4xy? Minus 3y. Minus 8y.
And that takes care of all the terms. Hold on. What's that equal to?
Would it be 4x plus 8?
Yeah. Now simplify the left. What's 9xy minus 4xy? Those are apples, both of them.
Would it be 5xy?
Keep going. It's minus 3 minus 8.
Minus 3, minus 8. So okay, I see. That would be negative 11xy.
11y.
Negative y.
11y. What's it equal to? 4x plus 8. Now this is the leap you have to make. What's the next step? Trying to solve for y.
Did you add 11 to...
Got to factor a y out. Notice what happens. If I factor a y out from the left, what am I left with?
Would be 5x minus...
What you're basically doing when you factor a y out is you're dividing both terms by y.
So it would be 5x minus 11?
Mm-hmm. Equals 4x plus 8. Now we're almost there. What's the next step? Trying to solve for y.
So, but if you distribute, you get right back.
No, you don't want to do that. We just undistributed it. In other words, when we factored a y out, we basically undistributed it. In other words, I violated my first rule, which was I added parentheses. But sometimes you have to, and this is a case where that's the only way to proceed. if I'm trying to solve for y, what is happening to y right now? It's being multiplied by 5x minus 11. So how do I get rid of the 5x minus 11?
You divide by 5x minus 11?
Yeah. If I divide by 5x minus 11, I'll always have to do it to both sides. Now I'm left with y, and that's the answer. So I was able to solve for y as a function of x. Not able to put a number on it, not with the amount of information they gave us. I'm going to close that out and reopen it because my computer seems to be having some difficulties. My drawing tablet, not my computer. That's why I kind of think that maybe there might have been more information on the right of that. Hold on a second. Because it looks like they were looking for a number, an answer. But you can't solve this. There's no numbers anywhere here. So x and y can be, you can solve for y in terms of x, but you can't solve for y or x alone. Okay, number 13. Now 13, they don't give you all the information, but what information did they leave out? And maybe that's what happened in 12. Maybe we were supposed to assume something. Maybe we were to assume that that was the midway line, which made 3y equal to 2y plus 2. Yeah, I'll bet they just forgot to put that instruction in there. Because they left out something in 13 also. What should they say in 13? How can I solve for x if I don't know something about these two triangles?
That they're similar?
Yeah, they don't say that. But the only way we can solve it is to assume it's true. They certainly look similar, so it's not a bad assumption, but there's no way to solve it if we don't know that they're similar. What's this 10 measure? Oh, the vertical, the altitude?
Yeah.
Oh, what equation comes out of this, if I know they're similar?
What do you mean? 20 is to 10 is 20, x is to 22.
22 is to 20. Oh, you did it the other way, okay. So you did the vertical compared to this vertical equals 22 divided by x. Notice we got x in the denominator. We can easily fix that by just switching everything. In other words, now that I notice I got x in the denominator, let's just reverse everything. Making it 10 is to 20 as x is to 22, that works. Now multiply both sides by 22 and there's my answer. Okay, so it's not a big thing, making sure x is in the numerator, but might save you a mistake at some point. Boy, when I hold my cursor an inch above my drawing tablet, it's acting like I'm pressing on the tablet. Might have to go out and buy a new drawing tablet here. 14. Notice, let's go back to 12 for a second. Notice that if I assume that that middle line, the middle of the three parallel lines, is a mid-segment line, then I can solve it. Because that gives me another equation that is independent of the ratio equation. In other words, I would be able to say that 3y equals 2y plus 2. That actually solves it all alone. That means y equals 2. So that solves it instantly. But they didn't put that information on there, so you can't... Oh, yes, they did. I didn't notice it. See the hash marks?
Oh.
I didn't notice it the first time through. But that makes it solvable in like one step. I can say 3y equals 2y plus 2. And that means y equals 2. So I don't even have to use the x's. I don't have to use any ratios. I don't have to do anything. Just got to notice that that length is equal to that length. I don't even need two equations. Although I'm not sorry we did it the other way, because I think you learned some stuff doing it with only one equation. Let me think about this one for a moment. Number 14.
We got number 14.
14, yeah.
Yeah, I'm looking at 14 trying to figure it out. We know a couple of things. We know that this angle is equal to that angle, which makes that line be a bisector. But that does experiment a little bit. We don't have any similar triangles, okay? So it's going to be hard to come up with a ratio. But
He's got an idea.
No, they're not similar.
So not similar. Okay, sorry.
That's okay. We know this. Oh, shoot. Let me unplug this and plug it back in again. Hold on. You don't need to go anywhere. I just need to unplug my drawing tablet. See if that will solve the problem. Which isn't an easy thing to do. I got to find the USB port in the back. Okay. Let's see if that solves my problem. I hope so. All right. It's tempting to say 15 is to 9 as x is to 3. But I'm not sure that that's true, and I can't really figure out why that would be true. The question is, if we take the big triangle and we bisect that angle, there is a relationship. In other words, if I make this angle up top here bigger, the one that I'm bisecting, then the only way I can make it bigger is to spread these two things apart, and 15 would get bigger, as would the base. So I think you can say that x is to 3 as 15 is to 9. Ooh, it bothers me though. I'm not quite sure why we can say that. It must have to do with this thing. When that bisects that angle, then it makes these proportional. In other words, it makes this length to this proportional, that to that. So what does that give me? 9x equals 45, x equals 5, which makes sense. It's not a fraction. All right. Why is that true, though? Let me think about that a moment. They're not similar triangles. They're not congruent triangles. Clearly, all three angles aren't equal. There just must be a theorem that I'm not remembering that has to do with if that bisects that angle, then these ratios all hold true. I don't want to take the time to look it up in the book. I'm 99% sure that this is the ratio that you get. There's really nothing else it could be. All right. Shall we go to 501, the next page?
Yes.
Okay, little trig. It's the tangent of A. Angle A being that angle right there.
It's going to be tangent 3.
Okay. You take trig functions of angles and you get ratios. Okay? So the most important thing about beginning trig is so, ka, toa. Remember that?
Yeah.
This tells you what the sine is, what the cosine is, and what the tangent is. The triangle they're giving me is a 3, 4, 5 triangle. Okay? So I'm going to draw it just like they have it. This is 3, this is 4, this is 5. And angle A is opposite the 4 side, so that's A. And C is opposite the 3 side, so that's C. That's got to be B. Okay. Notice how I did that. I think of angles being opposite a certain side. And that's a good way to think when you're dealing with trig or just geometry in general. Because a lot of times, if you're trying to figure out whether two triangles are similar, if they're not oriented the right way, it's very difficult sometimes. And so using sides opposite certain angles, if you can figure out which angles are the same, then you can figure out which are the corresponding sides. What does SOH mean?
Sin,
Sine?
which is opposite. Sine, yeah. Sine, which is opposite over hypotenuse.
Okay, what's CAH mean?
Cosine, which is adjacent over hypotenuse.
And TOA?
Which is that's tangent, which is opposite over adjacent.
Okay, so tangent of angle A is what ratio? Remember, when you take trig functions of angles, you always get ratios.
So would that be C?
No, C is an angle. You want ratios of side lengths.
Oh, side length. So it'd be 4. Or it'd be 4 and 3.
4 over 3. Just always give it as a ratio. Don't ever convert it to a proper fraction. Okay? In other words, trig is all about ratios. When you get the ratio 4 over 3, leave it like that. What's the sine of angle C?
Would it be 3 over 5?
Correct? And what's the cosine of angle C?
So that would be
It's a little tricky. Let's talk about what adjacent means. Because every angle has two adjacent sides, right? Angle C actually has 4 as an adjacent side, and so is 5. So which adjacent side are they referring to with this thing here? The one that's not the hypotenuse, always.
So it would be 4.
Correct. So cosine of C would be 4 over what? Remember, it's the adjacent over the hypotenuse.
So it would be 4 over 5.
4 over 5. There's a little hidden over right there in each one of them. The O does not stand for over. The O stands for opposite. Okay? Do you have any questions at all as to how to find the opposite side to an angle?
No.
Okay. It's just
Wouldn't it just be
take both rays and whatever line connects them, that's the opposite side to C. If you have a triangle like this, and that's A, B, C, and that's 2, 4, 11, what's the opposite side to A?
4.
And C?
2.
Okay. So solve for x in each of the problems, round to the nearest hundredths. When we see angles like 26 degrees or 46 degrees, that means it's a calculator problem. If this was 30 degrees or 45 or 60, then it's not a calculator problem. They expect you to know that without the calculator. But when we see odd angles that are not multiples of 30, 45, or 60, we know it's a calculator problem. So what equation solves this right triangle? Always start with the trig function on the left and then the angle. In other words,
would it be
go ahead.
Would it be sine, which is sine 26,
The trig,
17 equals
the trig function you want to choose is the one that relates the two pieces of information you have. Sine and cosine need a hypotenuse. We don't have it.
that would be tan 26.
There you go. In other words, the first step is to choose the right trig function. And then just complete the equation. What's the right side of it?
Would it be x over 17?
Which makes x equal to 17 times the tan of 26. And the one thing always to remember is that that's just a number that you're going to get out of your calculator. And you can do this all in one step on your calculator. You can say 17 times the tan of 26. And that's what x is. Okay, how about 17? If you
Hold on, David, hold on for a second.
Make sure
Can you
make sure you can do this in your calculator.
I want to make sure it comes up right.
What kind of calculator do you have, Patrick?
Yeah, Inspire CX-CAS.
Okay. That's easier even than the TI-84. I have a virtual TI-84 on my screen I can bring up, but let's make sure you can get it on your Inspire. Type 17 times, then hit your trig key on the left under the control button where it says trig.
Yeah, and then 26 in the parentheses.
Well, first of all, you have to choose tan because the trig key is going to pop open a menu that gives you 12 different choices.
Yeah.
Pick tangent and then type 26. And you should just be able to hit enter and it should give you a number.
You have to hit control enter, I think.
Maybe so, yeah. Let me do it on mine also, as long as I've got an Inspire also. So 17 times trig function tan
would be 5.19.
26. You don't need the ending parentheses. It puts it in there for you anyway. I get 8.29.
That's what you did.
Oh, yeah.
Oh, I thought you said 5.29.
Yeah, I accidentally put the wrong thing in the tangent for that.
There's another explanation as to why we might not be getting the same answer. What would that be? One of us might be in radians.
And one is in degrees.
Yeah, so I'm going to check, and on this calculator, it's pretty hard. It's not easy to figure out which you're in, but I know that the sine of 30 degrees is equal to 1/2. So I'm going to put the sine of 30, control enter, I get 0.5. That tells me I'm in proper mode. Type sine of 30 and see what you get.
Okay.
Just take your time.
I just have to get back to the calculator. 1 over 2. But I could also do
Now type 17 times the tangent of 26.
17 times 26.
Control enter.
8.29.
Okay. We're both in degree mode. There's a way to change to tangent or to radian mode, but you have to go to menu, and it's pretty difficult.
Document.
It's surprisingly difficult. This is such a great calculator. You would think that that would be automatic, and it's probably one of the biggest mistakes people make is not knowing which mode they're in, and it doesn't really tell you unless you go back to the menu. All right.
So David, that answer he gave you was correct?
Yes.
The
Same one I got, yeah. The first time I thought he said 5.19 or something like that. And that made me think that one of us was in opposite mode of the other. And they did want you to round this to 2 decimal places.
So would it be 8.3?
No. It would be, what your total answer was 8.29145, right?
Yes.
Okay, so to round it to 2 decimal places, the 9 rounds down, not up. It stays at 9, doesn't go to 10. So the answer is 8.29. Now, this is actually an excellent example of where you can get round-off error. Type tangent of 26 in.
I just got 1026 without pressing Control Enter.
I'm sorry, what?
I got 1026 without pressing Control Enter, so.
Okay, go ahead and get a number.
0.487733.
0.487733.
Yes.
Now, notice that if I round that off to 2 digits, it goes to 0.49, right?
Mm-hmm.
In other words, in this case, I have to round the 8 up because this number is 5 or greater. Now multiply that answer by 17. What do you get?
$8.29145.
Notice that's significantly different than what we had. We got 8.19. What happened? We had round off. In other words, when I rounded off the 4877 to 49, and then I multiplied it by 17, increasing the round off error by a factor of 17, now it rounds off to a different number entirely. That's why you should always, you could put that in as 2 steps. You could do tangent of 26 and then just take your answer and multiply it by 17 and then round it off and you're going to be okay. But you don't ever want to round off early in problems like this. You don't want to round off that answer and then multiply it by 17 because you take that round off error and you multiply it by a factor of 17. So it changes the final answer from if you hadn't rounded off early. Okay, what trig function am I going to use in problem 17?
Would it be cosine?
What are the two pieces of information they give us? Are they opposite, hypotenuse, adjacent? What are they?
Would it be adjacent hypotenuse?
X is 22 is adjacent, but remember that it's never adjacent if it's the hypotenuse. In other words, the adjacent side to that angle is right there. So what is X relative to that angle?
Would it be the
Opposite, right? Opposite over hypotenuse. What trig function is that?
Sine.
Sine. So I can say what?
Sine of 46 is equal to, would it be x over 22?
Uh-huh. And again, the best way to do these is not to get that and then multiply it by 22. The best way to do this is to multiply by 22 first, and then just put this whole thing into your calculator in one step. 22 times the sine of 46, and you'll get your answer with a control enter.
15.825.
What'd you get?
15.8255.
15.8255. Round that off to 2 decimal places.
Would it be 15.83?
Uh-huh.
Don't forget to round.
As long as this is 5 or more, go up. Anything less than 5, go down. Don't go down, but drop it. Don't round it up. Okay, 18. What trig function is going to relate those sides of 8 and 5? Is that right?
9 and 5.
9 and 5, okay. So this one's 9, that one's 5, and there's the, is that angle X?
Yes.
Okay.
I forgot what it was called, but it was sine with a -1.
Yeah, that's called inverse sine, arc sine, and let's talk about that for just a second. As I said, we take trig functions of angles to get ratios. If that statement is true, then this one's also true. The inverse sine of the ratio is equal to the angle. In other words, to solve for angles, we're always going to use inverse trig functions. To solve for sides, we're always going to use the trig functions.
So it would be,
So here we're solving for an angle. So first of all, what's the trig function that relates those? Did you say already? You said sine?
yes.
Okay. So there's a few ways I can do this. Let's start from the very beginning. Give me an equation that, without using inverse sine, what equation describes this triangle?
Would be 9 over 5.
Not quite. Always start with the trig function.
So it would be sine x
Of x, x is the angle, equals
9 over 5.
not 9 over 5.
5 over 9.
Right. Opposite over hypotenuse. Now, if that statement is true, then it means that x is equal to the inverse sine of 5 over 9. Now, there's a couple of ways to look at this. One way is, let's take the inverse sine of both sides. Well, when you take the inverse sine of the sine, you're left with just the angle. But also, that's by definition. In other words, I don't actually have to do this technique. If I just look at it, and I can see that if I'm solving for the angle, I want to take the inverse sine of that ratio. Always. Now, on your Inspire, pull up, hit the trig button.
And then under sine?
Under inverse sine. Notice that there's a sine and an inverse sine below it.
That's what I meant. Under sine, there's an inverse sine.
Right. Click the inverse sine, and then inside the parentheses, type 5 divided by 9. You might have to hit Control-Enter to get the angle.
Oh, that's 33.749. Could you also do it inverse sine 5 over 9 is equal to x?
Well, yeah, you don't need to. You don't need to set it up as an equation and let the calculator solve it. In other words, as long as we've got the x over here, is all we need is an answer to that question right there that I've circled. You know what I'm saying?
Yeah.
You don't really need to put it into your calculator as an equation. You just need to know what the inverse sine of 5/9 is. What if I said to you, the sine of that angle was equal to 1.1, or 11 over 10? Try doing that one in your calculator. Do inverse sine of 11 over 10. Doesn't like it, does it?
Nope.
The reason is that sines never give you an answer greater than 1 or less than -1. This is an impossibility. You cannot have the sine of an angle being equal to 11 over 10. And notice why. The hypotenuse always has to be the biggest side of a right triangle. So if the hypotenuse is in the bottom, what's in the top is smaller than the hypotenuse. So all sines of all angles are between -1 and +1. Same with cosine. So if you find yourself with this kind of a problem, it tells you that's either an impossible triangle, doesn't exist, but be aware of that restriction. That sines and cosines are always the answers, and not tangents. Tangents can go from negative infinity to positive infinity. But sines and cosines have to be between -1 and 1. Solve for the geometric mean of 2 and 9. How do I set that ratio up? What does it mean, the geometric mean?
Don't know.
Oh yeah, that would be.
That's what it means. In other words,
Just like,
it's 2 is to some number as that exact same number is to 9. So if they ask you for the geometric mean between any two numbers, if they said, what's the geometric mean between 7 and 11, I would say 7 is to x as x is to 11. So that's the way to solve for geometric mean. And then solve that.
would it be 18 is equal to 2x, x is equal to 9?
Cross multiply, what do you get? You get 18,
2x.
but you don't get 2x. You get x squared.
X squared.
It's x times x, right. You got it.
Keep forgetting that.
Yeah, but just those are the simplest rules you got to keep on top of.
So what's x equal to?
The
Square root of both sides.
all around.
Don't give it to me as a decimal. I'm not sure if these instructions.
Would it be 3 root 2?
Yeah, I wanted it. Very good. Square root of 18, which reduces to 3 root 2. So that's what the geometric mean is. And I don't believe they want you to give this as a decimal and round it off to 2 places. That's just, no. Only time they're going to ask you to do that is when they have these odd angles and you have to use trig functions and your calculator can't give you the answer as a radical, so it gives it to you as a decimal and then you have to round it off. But whenever you have problems like this, you can always give your answers in radical form, which is always better. Now, let's talk about any right triangle. Any right triangle. If you draw a vertical from this vertex, the vertex of the right angle, to the opposite side and make it an altitude so that it is a right angle there, you create three triangles. Triangle A, triangle B, and the big triangle C. They're all similar to one another. It's just kind of an odd property of right triangles. In other words, A is similar to B, and both of them are similar to the large triangle. But this is one of those cases where they're not oriented the same. Right? In other words, here, just to illustrate the problem that I'm talking about, I know that triangle 1 is similar to triangle 2. Give me the sides that are proportional sides. Which side is proportional to side AD? No, I'll make it easier.
Would it be AC?
Well,
Or were we talking about the big triangle?
hold on, let me start over again. Which side of the second triangle is proportional to side AB of the first triangle?
Would it be 80?
No, you want the hypotenuses. In other words, AB is the hypotenuse of triangle 1, right?
Yes, so it'd be DC.
So it'd be AC.
AC.
AC, yeah. In other words, if I wanted to start setting up ratios, I could say AB is to AC, that hypotenuse is to that hypotenuse, as, well, let's do the short side of that. BD is, what's the short side of triangle 2?
Wouldn't that be 80?
Yeah. In other words, what I'm trying to get at is that if your triangles are not oriented the same, and they're not here, this one's been rotated, basically, then you have to try to figure out corresponding sides based on something. And as long as I've drawn the triangle like this, it's easy to tell what the short side of this triangle is. It's BD. And it's easy to tell what the short side of this triangle is. It's AD. And when I say short side, every right triangle, there's the short side is one of the two acute. In other words, it's never the hypotenuse. That's always the hypotenuse. That's the short side, and that's the long side. Unless it is a perfect isosceles right triangle. If this side is the same as that side, then that's the only time that there's not a short side and a long side. Okay? So this problem might be a little difficult if I were to draw the big triangle as an isosceles triangle. But then notice what happens is it doesn't matter. If I draw it perfectly isosceles, so that that side's the same as that side, and there's my right angle. Now when I draw my vertical, this side is the corresponding to that side, because they're both hypotenuses. And now,
Hey, David,
Yeah.
isn't the hypotenuse of that big triangle that we're looking at
BC.
DC?
No. In other words, this is a right angle. It's the B. Did you say BC or DC?
BC.
Yeah, BC.
BC is the hypotenuse of the big triangle. But
Right.
notice there's three similar triangles.
Right, okay. So what you're talking about is
There's two, and there's ABC, the big one. All three of them are similar.
right. So 2 it would actually be AC, yeah.
So if I'm looking for corresponding sides, well, AB is the hypotenuse of 1.
Right.
AC is the hypotenuse of 2. And BC is the hypotenuse of the larger one, the original one. The trick on all of these is, in order to set up the ratios, you have to figure out what are the corresponding sides. And it's tricky when they're not oriented correctly. But all of this, I got a little sidetracked. The reason they ask you question 19 what the geometric mean is, it turns out that this vertical is the geometric mean in this picture. In other words, I can say x is to 15 as 15 is to 5. In other words, this is always your geometric mean. The thing that's in the denominator on the left and the numerator on the right. That's where your geometric mean goes. Remember when we did 2 and 9? We did 2 is to x as x is to 9. Well, there's your geometric mean that we can now solve for. Well, in this case, I'm sorry?
Oh, that was the computer.
Oh, okay. But that vertical that you draw to create these three similar triangles, that's always the geometric mean. So I know that that measurement of 15 has to go in the denominator there and the numerator there. And in the other two measurements, x is clearly bigger than 5. So the bigger number has to go x there. And now solving that, 5x equals 225, x equals 45. All right. Is that a comfortable place for you to stop?
Yeah, definitely.
Actually, don't you want to see if we can do the rest of these? Hey, David, is there any?
I looked at the rest of them. They're pretty simple. The thing I had a problem with was trig.
Are you sure?
Yes.
David, there's no possibility that we could extend maybe for another half hour. If I do it for another hour, is that be imposed on you? You don't need it? Are you sure?
Yes.
Patrick, don't bullshit me.
I'm sure.
Okay.
All
right, David.
That's fine. David, I'll only charge you for an hour and a half tonight. I don't like charging for time not done tutoring, and I haven't been doing that to you in the past. So
okay, well, I'm uncomfortable with blocking your valuable time and then not using it. So I appreciate it.
If it happens too much, I might change that policy. But
all right.
as long as it's not abused, and just every now and then it happens, then it's no big deal.
I'll leave it in your capable hands, and then you think that this is a good place to stop because you mostly wanted to do the trig function and got your help for that. All right, David.
I would actually think that Patrick would be better off doing 2 separate hours on the 2 days before a test rather than a 2-hour block on the day before the test.
I think that's a good idea.
I just think it avoids the burnout. In other words, you can only go so long without getting burned out on this stuff. And
exactly.
We're probably at that moment right now. And I really firmly believe that with all my students, not Patrick, but every student, who wants to do an hour of tutoring a week, I usually try to talk them into doing 2 half-hours a week because I think it's more effective. I think you get 100% focus when you do it that way, whereas when you do a full hour, a lot of my students, boy, they at the 45-minute period, they are so ready to be done that they're just not able to assimilate new information as well.
I think that's a wise statement, and I think we'll follow that from now on, because I think that's where he's at right now. I mean, he's just at the point where he wanted mostly to cover the trig. That was the part where he was a little bit shaky. He feels better.
I mean, it sounds like this has been an effective session, and I think he's learned a lot tonight. I just think in general, cramming I don't really think works as well as slow and steady. I just don't. I mean, you can make an argument that it might work better for tomorrow's test, but a week from now, it's not going to work better. In other words, a week from now, he'd been better off having 2-hour sessions than 1 2-hour session. And that I'm firmly convinced of.
I totally agree, and it's really is a confession. It's Patrick's propensity.
I don't know what your schedule is. I know you're always having to combine it with my schedule, so you do as you see fit, and I'm happy to do whatever it is you decide.
Yeah, no, I think, David, that's good advice, because it's actually Patrick's propensity to wait to the last minute and then say, I need, an hour and a half, 2 hours, or whatever.
It's not just Patrick, it's everybody. Everybody wants to do that.
I think it's human nature, but I think what you're
getting is they want their tutoring session to be as close as possible in time to their test.
Yep.
They figure 12 hours they'll remember it, whereas 36 hours they might not. But I actually think it works the other way around, at least for long-term memory, like I said.
I think that's true, David. So this is a great place to stop, and as always, we appreciate your help so much. We really do.
All right, David. Patrick,
good night.
David, have a good night, and I'll talk to you next time.
All right, thanks, David.
See you next time.
Bye-bye.
So I think that you had a good session, Patrick. There was a lot